We saw in the previous video that a dipole can result in an electric field. Now, in a real material there will obviously be lots of different molecules with lots of different dipoles and bonds. So it's a sensible question to ask how they might interact with one another. So we could picture, for example, that as in our previous example we had an electric dipole here, but then there might be some neighbouring dipole which in general won't be aligned with the original dipole. The first dipole generates an electric field, and we're asking the question, how does another dipole respond to that electric field? So that's the problem we're going to try and work out here. So if we think about the dipole that's shown in this diagram, an electric field interacting with the charge will result in a force. So this atom here is going to result in a force which is just going to be equal to the electric field times this positive charge. But obviously there's also an equal and opposite force here due to the negative charge, which is going to be equal to E times Q. It's obviously negative in this case. So the net force on this dipole due to the electric field is just going to be zero, because the force 1 is going to be equal and in the opposite direction to F2. So in general you always find that the net force on a dipole due to an electric field is going to be zero. However, it's not just the force that we need to consider, we also need to think about the torque. The torque is the force that tries to rotate an object. So if the dipole in our electric field is at some angle theta to the electric field, then there is going to be some kind of rotational torque that tries to align this dipole with the electric field. So the torque is in general a vector quantity again, and is given by the vector product of the distance and the force vector. In simple terms, what that means is that the torque is equal to the force times the perpendicular distance. Oops. So if we think about that for our example up here, the torque is going to be equal to 2, because there are two atoms, both of which are generating a force, times the force, which is just given by F in this case, and then the perpendicular distance is going to be half the length of this bond, because this is the point that we're going to be pivoting our little dumbbell dipole around. If the bond is d long, then half the distance is d over 2, and then the perpendicular distance between the force which is acting in the horizontal direction, so the vertical distance that we want, if we draw this triangle out, we have d over 2 between the pivot point and the charge. We have an angle theta here, so the one we want is d over 2 times the sine of theta. So we've got d over 2 times the sine of theta. So if we then work out, sorry, there shouldn't be a vector here. So if we then work out that, we can substitute for F is electric field times charge. The 2's are going to cancel, and so we're going to end up with a torque that's equal to E times Q times D times the sine of theta. That's the torque. So the work done to rotate that, the change in energy, I'm going to write as U, so that's going to be the work done to rotate the dipole. So U is just equal to the integral of the torque times d theta, which is equal to the integral of the torque, which is EQ d sine theta integrated with respect to theta. So the integral of sine is just minus cos. So u is equal to minus e qd cos theta. We can, for convenience, define a new vector which we're going to call the dipole moment, which is p. So define p as a vector is equal to q times d, and then we're going to introduce a little unit vector, and the unit vector is going to act in this direction along the line that's joining the two charges. So this is the dipole moment. Okay. If we do that, then we can simplify the equation to say that the energy change is equal to minus this new vector that we've described, the dot product of that with the electric field vector. So the dot product of two vectors is going to give us a scalar, which is what we need to get an energy. And the reason we can write that is because of the definition of the dot product, which is that P dot E dot is equal to the magnitude of P times the magnitude of E times the cosine of theta. So P is our Q times D, then we've got the cos theta and the E, and just a minus which drops out here. So we get this nice identity that the energy to rotate a dipole is related to its dipole moment, dot product of that with the electric field. Having done that, we're going to now move on to discuss polarizability. So up until this point, we've only considered what are called permanent dipoles, and these are dipoles that arise due to the electronegativity of one of the atoms in the molecule. And so even in the absence of an electric field, there is a separation of charge that occurs inside these molecules. However, that's not always the case. Sometimes you can have a neutral atom or a molecule where, in the absence of an electric field, the charge is completely uniformly balanced, and therefore you don't end up with an electric field. However, when we apply an electric field to this atom or molecule, what that does is it results in the generation. It generates a dipole because the electrons will want to shift slightly as a result of the electric field in the negative direction, and the positive charge will be slightly more exposed in the other direction on the electric field. So when we apply an electric field, that will distort the electron cloud. But obviously, at the same time that we do that, we're generating a separation of charge in which we've got a minus Q here and a positive Q here internally within the atom or molecule, which are going to attract one another. So the electric field wants to distort as much as possible and pull the positive and negative parts of the atom as far apart as possible, but the Coulomb attraction between this negative part of the electron cloud and the positive charge is going to want to pull things back together and generate something that looks much more like the neutral atom. So there must be a balance between these forces. So effectively what we do is we balance the external force, which is due, it's hardly legible, the external force which is due to this electric field with the internal force which is going to be due to the Coulomb attraction. So the external force is due to the field. We've seen that before. It's just equal to the charge times the electric field that's being applied. And then the Coulomb force we're also familiar with the equation for, which is going to give us minus the charge squared divided by 4 pi epsilon naught times d squared, which is the separation of the centre of mass, if you like, centre of charge of these charges. And then we need a unit vector that's acting along the direction in which these two things have been separated. If we just rearrange that slightly, we can cancel one of the Q's. We end up with that the electric field is equal to, that's the external electric field, is equal to Q over 4 pi epsilon naught d squared r hat. But as we saw earlier, we can define this vector called the dipole moment, which is equal to the charge times the separation of those two charges times the unit vector. That can be rearranged to say that p bar over d is equal to q r hat, and then we can then substitute that into this equation, because here we have a q r hat, and so we can substitute p bar over d for that. So the electric field is the same thing as the dipole moment divided by 4 pi epsilon naught d cubed. Rearranging that in terms of the dipole moment, we get 4 pi epsilon naught d cubed times the electric field. And again, this term here is given a special name, which is the polarizability, which is often written as an alpha. And this polarizability tells us something about how easily we can separate charges within a molecule. How much of an electric field do we need in order to generate a specific type of dipole moment? And you'll notice that it's related to the length scale here. So in general, what we find is that polarizabilities scale with the volume of the electron cloud. So bigger atoms, bigger molecules tend to become more easily polarized when we apply an electric field to them. At the end of this video, I just want to try and draw some threads together from the few previous calculations that we've done, and try and look at what the implications of that might be. So we looked at the fact that in one of the previous videos that when you have a permanent dipole, it will generate an electric field at some point because of the fact we have a separation of charges inside the molecule. Then in the next section, the first section of this video, we start to think about, well, how does that electric field influence other other molecules within a sample? So in general, it's not true that the dipole moments in general don't have to be aligned, but what we've seen is that there is actually a force that's being generated by an electric field due to one atom that is going to try and rotate different molecules so that they align with one another. So there's a tendency within materials for these different dipoles to align with one another, and when they align with one another, that means that effectively we have an attractive interaction between the different molecules, because the minus Qs and the plus Qs will be close together, and so there's an attraction due to permanent dipoles in materials. However, in the last part of this video, we saw that even atoms that are neutral and therefore have no permanent dipole can be made to have a dipole because of the presence of an external electric field. So if we take an atom that has some dipole, if we draw it now as an electron cloud, then this will also generate an electric field. So if I stick an atom which is completely neutral next to an atom that has some dipole, because of the electric field of this atom on this atom, it will actually start to create a separation of charge even within a neutral atom. So imagine a piece of material in which we had all neutral atoms. The picture we've drawn is very static here, in which things are completely rigid and either permanent dipoles or not dipoles at all. The reality is that these electron clouds are continually fluctuating around atoms, and so on a very small timescale, what we'll find is that at one particular moment, one atom may have a slight positive charge on one side and a slight negative charge on another side. But in that moment, it generates an electric field which influences its neighbouring atoms. And so even when we have a material that's composed of neutral atoms, there can still be attractive forces that are generated by these induced dipole forces, which is something we'll go on to look at in some of the later topics in this lecture. But this is a fascinating bit of physics. It shows how permanent dipole forces are actually still present even within these neutral atoms, because of these fluctuations in the electron clouds, generating an induced dipole. And so the alignment of these interactions will happen in much the same way as it does with these permanent dipoles, and we'll end up with induced dipoles that attract one another between neutral bits of material.